This section discusses regression equations. It also introduces many basic concepts on regression. Let's look at one example. The table displays data on age and price for a sample of cars of a particular make and model. Ages are in years, prices are in hundreds of dollars, rounded to the nearest $100. From the table, we can see that there are 11 total cars. For each car, we have its age and price. In order to visualize the data, we draw a plot on the right. The horizontal axis is age and the vertical axis is price. Each point corresponds to a car. We draw the point corresponding to its values of age and price. For example, for the second car, its age is 4 and its price is 103. The corresponding point on the graph is the one with x coordinate 4 and y coordinate 103. We can observe from this plot that as age of a car increases, its price decreases. There is roughly a linear trend between the relationship between price and age. The points do not fall exactly on a straight line, but loosely fall around a linear pattern. There are many similar problems in practice. A response variable is the variable to be measured or observed, and a predictor variable is a variable used to predict or explain the value of the response variable. In the example we just discussed, the response variable is the price of a car, and the predictor variable is the age of a car. We are mainly interested in the price of a car. The price of a car can be predicted by its age. The plot we drew in the previous slide is a scatter plot, which is a graph of data from two quantitative variables of a population. When drawing a scatter plot, we place the response variable on the vertical axis and the predictor variable on the horizontal axis. Each point in the graph represents one individual in the dataset. Let's use this example to introduce regression equations. Suppose the dataset contains 3 observations, which are displayed in the table. Now, we want to use a straight line to catch the pattern of this dataset. There are many possible choices of lines. For example, we draw 2 possible lines on the slide. Now, we need to figure out which line is better. Let's introduce some concepts. A prediction is the predicted value of y by the line. It is denoted by y hat. If we have a value of x, use this linear equation, we can calculate a value of y. This value of y is the prediction of the corresponding value of x. A prediction of y may or may not be equal to the observed value of y. Their difference is an error. We use E to denote it. An error is the signed vertical distance from the line to a data point. If the data point is above the line, the error is positive. If the data point is below the line, the error is negative. Here, we do some calculation for these 2 lines. The first line, A, is y equals -1 plus 2x. When x equals 1, the predicted value of y is y hat equals -1 plus 2 times 1 equals 1. The error can be calculated as E equals y minus y hat equals 2. We can do similar calculations for the second line, B. The linear equation is y equals 1 plus x. The predicted value of y is y hat equals 1 plus 1 equals 2. The error is E equals y minus y hat equals 1. We can calculate the predicted value of y and error for all data points for line A and B. The results are displayed in the table. The errors can be positive or negative. In order to aggregate them together, we square them and calculate their sum. The sum of squared error is 8 for line A and 6 for line B. The second line has a smaller sum of squared error. The least squares criterion is that the line that best fits a set of data points and is the one having the smallest possible sum of squared errors. A regression line is the line that best fits a set of data points according to the least squares criterion. A regression equation is the equation of the regression line. We can derive a formula to find regression equations. Here, we ignore the mathematical details and only present the formula. Denote the regression equation as y hat equals b0 plus b1x. The slope b1 is sxy divided by sxx, where sxx is the sum of squared xi minus x bar, and sxy is the sum of the product of xi minus x bar and yi minus y bar. After we calculate b1, we can calculate b0 as y bar minus b1 times x bar. Let's try to apply this formula to calculate the regression equation for this data with 3 observations. First, we can calculate the sample means x bar equals 2 and y bar equals 3. The table calculates xi minus x bar and yi minus y bar for each observation. We then calculate sxx and sxy. The slope b1 is therefore sxy divided by sxx equals 1. The y-intercept is y bar minus b1 times x bar equals 1. Therefore, the regression function is y bar equals 1 plus x. It is the line B in the previous slide. In practice, we seldom calculate a regression equation by hand. In most cases, we will use software such as Excel to calculate it. In the example of age and price of cars, suppose that we calculated the regression equation using Excel. The regression equation is y hat equals 195.47 minus 20.26x. We can use this regression equation to predict the price of a car if we know its age. For example, for a 3-year-old car, its predicted price is y hat equals 195.47 minus 20.26 times 3 equals 134.69. For a 4-year-old car, its predicted price is y hat equals 195.47 minus 20.26 times 4 equals 114.43. Because the slope of the regression line is negative, price tends to decrease as age increases. The slope of negative 20.26 indicates that cars depreciate an estimated 2,026 per year, at least in the 2 to 7-year-old range. When using the regression equation for prediction, we need to be very careful about extrapolation. Extrapolation means using the regression equation to make predictions for the response variable outside the range of the observed value of the predicted variable. Grossly incorrect predictors can result from extrapolation. For example, the relationship between y and x may be a complex pattern as shown in the graph. If we only collect data for x in the range of x1 and x2, we may find that a linear equation can fit the data very well. However, if you try to apply the regression equation beyond the range of x1 and x2, you will get a misleading result. We can illustrate the problem of extrapolation in the example of age and price of cars. The regression equation is y hat equals 195.47 0.47 minus 20.26x. For an 11-year-old car, the value of x is 11. Replace x by 11 in the regression line, we get y hat equals negative 27.39. The price of a car cannot be negative. It does not make sense. It indicates that the regression equation is not applicable for x equals 11. In fact, in the data, the range of age is between 2 and 7. If we want to apply the regression equation for prediction, we should restrict ourselves in the range of 2 and 7. To help avoid extrapolation, we may include the range of the observed values of the predicted variable with the regression equation. An outlier is a data point that lies far from the regression line, relative to the other data points. An influential observation is a data point whose removal causes the regression equation to change considerably. In applications, we usually need to try to find outliers and then check whether they are influential. For example, in the example of age and the price of cars, the ninth observation is an outlier. Its price is 169, which is clearly larger than the prices of remaining cars. We can calculate the regression equation twice. First time, use all observations. Second time, remove the ninth observation and calculate the regression equation. The two lines are displayed on the graph. It is clear that these two lines are quite different. We can conclude that this observation is influential. An influential observation is usually an outlier. However, an outlier is not necessarily an influential observation. These two graphs illustrate this claim. In each plot, the point on the far right is an outlier. We draw two regression equations, one from all observations and one from the observations with the outlier removed. In the first plot, the two lines are similar. It is simply because the outlier happens to lie on the linear trend of the remaining points. Therefore, it does not matter with or without this outlier. In the second plot, the outlier does not follow the pattern of the remaining point. Therefore, it will influence the regression equation when we remove it. In practice, we remove influential observations if they are due to a measurement or recording error, not belonging to the dataset. If no explanation for the influential observation is apparent, the decision whether to retain it is often difficult and calls for a judgment by the researcher. Before finding a regression line for a set of data points, draw a scatter plot. If the data points do not appear to be scattered around a line, do not determine a regression line. As demonstrated in the plot, the points have a curvature pattern. It is misleading if we use a regression equation. Additionally, drawing a scatter plot also helps us find outliers.